So let's do an example problem of a surface integral, okay? Calculate the surface integral of x ds. So this is already showing an example of using x, where the surface is the part of the sphere x squared plus y squared plus z squared equals r squared. So this is a sphere of radius r, right? You know the equation of a sphere. But the part of that sphere in which x is positive, y is positive, and z is positive, i.e. the first octant. Okay? So as usual, I recommend some intuition for what is happening. So I have plotted the first octant of a sphere. So we are in this octant of space where x, y, and z are all positive, okay? And then I decided to plot on the surface of this sphere, which has a radius r. So remember, the radius r will be this will be z equals r, this will be x equals r, and this will be y equals r. So I decided to plot on the surface of this sphere the value of the integrand. So the integrand is x. So the function that is being integrated is a function of x, y, z, which is given by x. Okay, so here x is going between 0, actually this should be r, between 0 and r. Okay, so this means that any point in the sphere in which x equals 0, for example, in this line here, in this arc here, x equals 0, and therefore the integrand is 0, and that's why this is blue, dark blue. Then as you increase x, you get concentric circles around this pole. Okay, so you could call this, it's not the North Pole because it's not on Z, but it is a pole, I don't know how to call it, it's a point in this sphere where x equals r. And you have seen that as we moved towards that pole, the color was getting darker and darker because the integrand x is getting bigger and bigger. Okay, so now we are doing the surface integral of x ds. So maybe x was the density. So this sphere is just like a plate, which is heavier here, and it's less heavy, until here it doesn't even have any weight. Okay, at this exact line there is no weight. And maybe you are calculating the total mass of this plate. So that's why you are doing the double integral of x ds, if you imagine that x was the density. Okay? So this problem doesn't say what this function is. We are not calculating a mass, we are just calculating a surface integral. Okay? So that's the intuition of what's happening. So let's do the calculation and let's follow the steps in the recipe. The first step was to parameterize the surface. So in order to parameterize the surface, we are going to use spherical coordinates. But we are going to fix the radius. So we are using r, which is the radial coordinate. We are going to fix it to capital R, which is a constant. Okay. So then you look up the position vector in spherical coordinates, and you are given that table in the exam, and you substitute little r equals capital R. So you find that the parameterization of your surface is this: r sine theta cos phi, r sine theta sine phi, and r cos theta. Okay, and this is your parameterization. So this parameterization means that this is equal to x, which is a function of theta and phi, y, which is a function of theta and phi, and z, which is a function of theta and phi. Okay, and the total vector r, let me give some space here, the total vector r is a function of theta and phi, which play the role of our two parameters u and v in all of the recipes and equations. Okay, great. Are we finished with the first step? No, don't forget to give the limits of integration. Okay, so in this case we have this octant of the sphere, so we have to think a little bit. So when phi equals 0, we are here, where we are on this line, and as we increase phi, we move through these lines in succession. So each of these lines has a bigger phi until we reach this point, which corresponds to an angle phi equals pi over 2. Okay, therefore phi is changing between 0 and pi over 2. What about theta? So theta is the angle with the z-axis. So for example, at this point we have the z-axis and we have the vector joining the origin with this point. So this angle is theta. So clearly this angle is changing between 0 and pi halves. Okay, so theta is changing between 0 and pi halves. So that's why it's very important to write the limits of the two parameters. Okay, so that's step 1 finished. Step 2, find ds. In this case, this is a sphere. I have done many problems. I have demonstrated to you how to calculate ds, and I just remember it. ds is r squared sine theta d theta d phi. And that's fine. You don't need to justify this. It's a well-known result. Okay? Third step, we evaluate the integrand at the surface. Okay? So we have our function, which is being integrated, and the function is x. So the integrand is x ds. We need to evaluate it at the surface. So what does this mean? It means that we cannot have an x here, because x changes when we move through the surface. So we need to write x as a function of u and v. So how do you do that? You go into your parametric equation of the surface. X is a function of theta and phi, this function here. So we need to substitute x with this, r sine theta cos phi. Times ds. Okay, so this is now the function evaluated at the point. Okay, so this was the function in terms of x, y, z, and now we have the function in terms of theta and phi. So we managed to do this substitution. And finally, we perform the double integration. So the nice thing is that at this point, when we substitute x ds, that was the original integral we wanted to calculate, right? So when we now substitute everything, we substitute the third step here. So this is the double integral of r sine theta cos phi. And now times ds, and ds we take it from the second step, r squared sine theta, r squared sine theta d theta d phi. That's ds. So notice how the fourth step gets information from the third and the second steps, yeah? And even from the first step, because now we have to write the limits of integration. And we have here d theta and d phi, which means that here go the limits for theta, which are 0 to pi over half from the first step. And then d phi, which means that the limits of this outer integral must be the limits that we wrote for phi, 0 to pi halves. And now the sanity check that I told you earlier, this must be a function only of the two parameters. A function of theta and phi only, plus constants. Is this correct? Yes, this is correct. We only have sine theta, cos phi, sine theta, d theta, d phi, which is expected, and then we have some constants around. So everything is ready for the integration. Okay? So let's do it. We can keep the r cubed outside, because that is a constant, so that can go outside. And then we have a function of theta multiplying a function of phi. So we can do separation of integrals. Remember that, right? So we can do r cubed times the integral for theta, which will integrate the sine squared of theta d theta, times the integral for phi, which has the same limits, but now we have cosine of phi, d phi, okay? And these are integrals that you know how to do from the first semester maths. These are normal integrals, okay? Let me, in any case, refresh you how to do this kind of integrals. They are very common in the second semester to have, for example, the integral of sine squared. So let me copy this on the next page and let me solve it for you. So how do I do the integral of sine squared? The easiest way for me is to remember that sine squared can be written as 1/2 minus 1/2 cosine is 1/2, yeah, minus 1/2 cosine of 2 theta. Okay. How do I remember this? I have a little trick, and I must confess I always do this trick. So I literally, in my head, I remember how the function sine looks like from 0 to 2 pi. So the sine function looks like this. Okay. So then I say, okay, how does the square, so this goes from 0 to 1 and to minus 1. How does the square of this function look like? So the square of this function, well, near the origin, the function looks like a straight line. And when you do the square of a straight line, you get a parabola. So near the function, you get a parabola like this. Then when it reaches 1, 1 squared is still 1. So we reach 1. Then we go back to 0, and 0 squared is also 0. And also we have another straight line here, which becomes a parabola. So this becomes like this. Then we reach minus 1, and minus 1 squared is 1. So we reach positive, and then 0, and we continue like that. Okay? So I always remember that sine squared looks like a sine wave, except that instead of going from minus 1 and 1, it's going from 0 to 1. And that's very easy to remember. Okay? And also it's easy to remember that it will have twice the frequency, or the period is half of the period, right? Because here you have one peak and one trough in 2 pi, while in the square you have one trough, one peak, and the other half of the trough, and then one peak and another half of the trough. So you have 2 peaks and 2 troughs in 2 pi. So it's double the frequency. So then it's very easy for me to write the equation for this thing that I always picture in my head. I picture it has to start at 0 and it has to go to 1. And I know that the average, this is going to be a function that is around 1/2. Right? So this line is 1/2. So then I know that this function is 1/2 plus either a cosine or a sine of amplitude 1/2, because this goes up by 1/2 and it goes down by 1/2. So I know that the amplitude of this sine or cosine is 1/2. And now the only question is this a sine of 2 theta or a cosine of 2 theta? Which one is it? So then I have to think about, it starts at 0. So when I substitute theta equals 0, I need to get minus 1. Okay. So therefore, this has to be minus 1/2 cosine. So I write this. Okay. Anyway, you can use whatever method you want to do regular integrals. I'm just revealing my thought process when I try to integrate sine squared. Okay. So in any case, you can just look it up and just substitute it directly. Fine. But the good thing is that now this is very easy to integrate, because the integral of 1/2 is just a half theta, and the integral of minus a half cosine 2 theta is very easy. It's just minus 1/4 sine of 2 theta. Evaluated between 0 and pi fourths. Okay, so this is equal to pi eighths minus the sine of 2 times theta is the sine of pi halves, and the sine of pi halves is 0, so this is minus 0. And then minus 0 minus the sine of 0 is 0. So the end result is pi over 8. By the way, here, oh, sorry, this upper limit should be pi over 2, which means that this wasn't pi over 8, it was pi over 4. So the final answer is pi over 4. Okay, so that's for the first integral. Now for the second integral, that's very easy. The integral of cosine is the sine evaluated between pi over 2 and 0. So this is equal to the sine of pi over 2, that's 1, minus the sine of 0, that's 0. Okay? So therefore this is equal to 1. So finally I can write the total thing as pi fourths times r cubed. And that is the final answer to our integral. Okay? So I hope that was clear. I think I spent as much time in doing the integrals as I spent in explaining the procedure. But anyway, it's always good to refresh how to do integrals. So see you in the next video or next example.